So we'll start with a theorem. The general solution of the non-homogeneous differential equation AY double prime plus BY prime plus CY equals G of T can be written in the form Y equals YC of T plus YP of T. So this is the complementary solution. Or in other words, it's the general solution to the corresponding homogeneous differential equation. And Yp of T is the particular solution. And this particular solution is going to depend on the form that this G of T takes. So let's write that down in words. Where Yc of T is the corresponding general solution, is the general solution to the corresponding homogeneous differential equation. And Yp of T is a particular solution to the non-homogeneous differential equation. And if you think about it, this makes sense because really you could think of this as AY double prime plus BY prime plus CY equals G of T plus 0, right? So the complementary solution will get you the plus 0 part, and the particular solution is going to get you the G of T part. And so how do we find this Yp of T? We know how to find the Yc of T. We did that before in previous sections. So how do we find this particular solution? Well, it's going to depend on the form that the G of T takes. So how can we find Yp of T? Well, the structure or the form of Yp of T will depend on what the G of T. So it depends on the form of G of T. So let's get some different cases. Say G of T is some CE to the RT. Case 2, say G of T is C sine T or C cosine T. Case 3, say it's some product of these two kinds of things. CE to the RT sine T or CE to the RT cosine T. Case 4, let's say if G of T is some polynomial. Okay, so we'll talk about these different cases. So here's an example. So let's say we want to find yp of t for y double prime minus 3y prime minus 4y equal 3e to the 2t. Solution. Okay, so since the characteristic equation r double prime minus 3r, r squared, minus 3r minus 4 equals 0 has roots r equal 4 and negative 1, we have that yc of t, the solution to the corresponding homogeneous differential equation is going to be c1 e to the 4t plus c2 e to the negative t. Okay, we did that sort of thing before. So to find yp of t, we know it must be of this form. It needs to be of this form. Yp of t needs to be equal to some a e to the 2t. Now, why is that? Because when I take the second derivative of that thing minus the 3 times the first derivative minus 4 times that thing, I end up with some kind of constant times e to the 2t. So the only way to end up with that on the right-hand side is if the y, part of the y, had some kind of e to the 2t thing in it. Okay, so I'll give you a theorem about that in a little bit, but for now, let's just say our yp is of that form. So if yp of t is equal to a e the 2t, then yp prime of t, just take the derivative, is going to be 2a e to the 2t, and yp double prime of t is going to be 2 times 2 is 4a, oops, big A, e to the 2t. Okay, good. So let's plug all this into the differential equation. Plug that into the differential equation, and we get, okay, so y double prime is 4a e to 2t minus 3 times 2a e to the 2t minus 4a e to the 2t, and that all needs to be equal to 3e to the 2t. So what do we end up with here? We end up with 4a minus 4a minus 6a, so we end up with negative 6a e to the 2t needs to be equal to 3e to the 2t. In other words, 6a, negative 6a needs to be equal to 3. The coefficients of the e to the 2t need to be equal for this to work. In other words, a is negative 1/2. Okay, so what does that tell me? That yp of t is going to be equal to negative 1/2 e to the 2t. So our general solution is going to be of this form: y equals c1 e to the 4t plus c2 e to the negative t minus 1/2 e to the 2t. So you can see the structure of this is we have this yc of t, and we have this yp of t. Notice that the yp of t part, all the constants have been solved for, so we've figured out what the constants are for that particular part. That's why it's called a particular solution. And then the corresponding homogeneous part has those coefficients. Now, C1 and C2. Now, if I were given some information at the beginning about some initial values, then I could solve for those C1 and C2 coefficients at this point, but I don't have any of that information, so I can't solve for the C1 and C2 here. So let's find a solution. Oops, I'm still writing in red. Let's find a solution to this differential equation. Okay, so our characteristic equation is r squared minus 3r minus 4 equals 0. So that gives us the solutions r equal 4 and negative 1, same thing we had before. So our yc of t, again, is c1 e to the 4t plus c2 e to the negative t. Okay. So our yp of t, since I have this over here is my g of t, my yp of t is going to take the form a sine t plus b cosine t. So you may wonder, okay, my g of t only has a sine in it. Why should my particular solution have a sine and a cosine? Well, if you think about it, the derivative of cosine is sine, right? So I could have some sine parts and some cosine parts, and then when I take the first and second derivatives, I end up with sines and cosines in those first and second derivatives, and somehow, having this little bit of a cosine part could end up giving me something that has a sine in it eventually after taking derivatives and subtract everything out. So, so you end up that you have to have both the a sine t plus the b cosine t. So all of that can be part of that particular solution. So let's go ahead and take the derivative and see what we get. Yp prime. The derivative of sine is cosine. The derivative of cosine is negative sine. Okay, and yp double prime is going to be negative a sine t plus minus b cosine t. So I'm going to plug all of that into my differential equation. And that gives me, okay, y double prime, so negative a sine t minus b cosine t minus 3 times y prime, which is a cosine t minus b sine t. And then I want to do minus 4 times y, which is a sine t plus b cosine t. And I want to set that equal to 2 sine t. Okay, so what I want to do now is multiply everything out and combine all of the like terms. So I end up with negative a sine t minus b cosine t minus 3a cosine t plus 3b sine t minus 4a sine t minus 4b cosine t equal to sine t. Okay, so what's the coefficient of the sine? I can take all the things with sine together and I can get negative a. Let's see, where are all the things with sine in it? This one, and that one. Okay, so we get negative a plus 3b minus 4a sine t plus, and then what's the cosine stuff? I have negative b minus 3a minus 4b. Okay, so this is going to give me two equations in A and B. Clearly the coefficients of sine need to be equal to each other on either side of the equal sign, so I know that this coefficient here needs to be equal to 2, and this coefficient here needs to be equal to 0, which is the coefficient of cosine on the right-hand side. So I get that negative 5a plus 3b needs to be equal to 2, and I get that, let's see, negative 3a minus 5b needs to be equal to 0. That gives me two equations and two unknowns in a and b, which I can solve. And I'll just spare you the algebra, and we'll just say a is going to be equal to negative 5/17, and b is going to be equal to 3/17. So that gives me the particular solution. Yp of t is equal to negative 5/17 sine t plus 3/17 cosine t. And so our general solution is going to be equal to our corresponding homogeneous solution, c1 e to the 4t plus c2 e to the negative t, plus our particular solution, negative 5/17 sine t plus 3/17 cosine t. So we have our corresponding homogeneous part and our particular solution there. Okay, I'll do one more example of this type. So, whoops, I'm writing in red again. So we want to find a solution for y double prime minus 3y prime minus 4y equals negative 8e to the t cosine of 2t. And if you'll notice, this left-hand side is the same as the previous two examples, so the corresponding homogeneous solution is going to be the same. So here's our solution. As before, our yc of t is equal to the same thing we had before, c1 e to the 4t plus c2 e to the negative t, because that left-hand side hasn't changed. It was the same in the previous two examples. Okay, so we saw that. So if I look here at the left-hand side, I can see that'll give me a clue as to the form of my particular solution. So yp of t has the form, so our ypt has the form a e to the t cosine 2t plus b e to the t sine 2t. Okay, now this one's going to be fun to take the derivative of, because it's going to explode on us. We have to do product rule a bunch of times. Okay, we can do this. So yp prime of t is going to be what? All right, I'm going to have to use product rule. So we'll do a e to the t cosine 2t plus a e to the t times negative sine of 2t times 2. All right, so that's the derivative of that first term, plus, now let's take the derivative of the second term. So I have, again, product rule. The derivative of b e to the t is b e to the t. We'll leave sine 2t alone, plus, then we'll leave the b e to the t alone, and we'll do cosine of 2t times 2 from the chain rule. So it got kind of bigger. And now we'll take the derivative again, and we'll have even more terms. So I'll have a e to the t cosine 2t plus a e to the t times negative sine of 2t times 2. All right, that's the first term. Plus, oh gosh, anyway, you're going to get a whole bunch of terms here, right? So this part here that I just took the derivative of was the derivative of that term. So now I need to take the derivative of each of those 4 terms. I'm going to get up with eight things here. It's going to kind of get big, and then once I combine like terms, it will shrink down again. So basically the idea is that I want to take that yp double prime, yp prime, and yp, plug it into this differential equation here, and then I want to equate the similar coefficients, the like coefficients, and solve for the a and the b. And once I do that, that will give me my particular solution. So I'm going to save us all of that work and stop there. But I will tell you the answer, that A ends up being 10/13 and B ends up being 2/13, so you can verify that on your own.